No, they don't really exist. They are really just some I would say mathematical artifact of using finite basis set. That's what I'll come to that also later. Why we call virtual? This actually I don't know. It's just everyone now using virtual, but they are just unoccupied. Yeah, it's just a name. Yeah, yeah. But okay. Um, no. But yeah, maybe I don't know if I answer completely your question, but if you say, okay, I take one electron from the occupied and I put in the virtual, and that's my excited state. So for example, let's say we take helium. So yeah, there is only one occupied orbital, the 1s, and then you get a bunch of virtual. The second orbital that is not occupied, that's not the 2s of helium. Okay, that answer your question? Okay. Hmm. Okay, so really this second orbital, it's not the 2s of helium. Okay, actually you could see it as more like the 2s of helium minus, but even that is not that correct. Hmm. Okay, other questions? No? All good? All right, so that's the theory. Now, if you want to implement it in a computer, you need to put some numbers, right? The matrix should be numerics. You cannot just say, okay, give me the spin orbitals. You have to explain how you're going to describe these spin orbitals. There are several ways to do it, but in most quantum chemistry package, we use, so you need mathematic functions, right, to describe these spin orbitals. And in most quantum chemistry package, we use Gaussian functions. So we write each orbital as a combination of Gaussian function. Okay, so you get like x n y m z l exponential minus alpha r minus r squared. Okay. And what you optimize, so as I said, what we want in Hartree-Fock is to get the smallest, the lowest energy possible for the electron energy. So the parameter that you want to optimize are those guys. So that's this coefficient here. So what you tell the computer is, okay, use the basis set with this exponent alpha. So you get like a bunch of Gaussians, say 10 Gaussian with 10 different exponents. And then you say, okay, now find me this coefficient C that gives me the lowest energy. Okay? Yeah. Yeah, to the lowest energy. So it's a now it's just a optimization problem. You have to find you are in this space described by the Gaussian, and you try to find the position in this hyperspace space where the energy is lower. There was a question also. It's a good question. That's my next. Yeah. So, and this is I'm confusing. Yeah. Sorry. Okay. Then I'll answer to those two questions now. Okay. And that's when you start quantum chemistry. That's the confusing part because quantum chemists they like to use a lot of acronyms. I guess it's true in many fields, But in quantum chemistry, that's really we overuse acronyms, and when you enter, when it's your first time, it's confusing. Okay, so how do we choose these alpha parameters and how many Gaussian we include? People have done the work for us. So there are a large number of basis sets that are optimized for every atoms. So there is a database, it's the EMSL database, where you can go, you have this Mendeleev table, you say, okay, I want the basis set for carbon, you click on carbon, and then you have a list of acronyms, okay? And there are actually a hierarchy of basis sets. So we know, for example, there is a kind of basis set that we call Dunning, so it's a U. Okay, so we call it Dunning because Dunning was the guy that optimized those parameters. So they optimized those exponent and chose this NLM and so on for us. Okay, and they have names which are kind of weird. We have, for example, CCPV DZ. So for the DZ stands for double zeta. So it's correlated, consistent, polarized, valence, double zeta. What is really important is this double zeta actually. Okay, but there are also CCPV triple zeta and quadruple zeta and so on. Okay. And for each of them, you have a set of exponent for your Gaussian, and the double zeta has less Gaussian than the triple has less than the quadruple less than the CCPV 5Z. Okay, it's just one kind of example. There are other kind of basis set. There are more complicated, augmented, CC, and so on. Again, I'm not going to go into detail for that. It's just, again, to give you an idea, a feeling. Okay? So this is how you do it. So we know that triple is better than double, quadruple better than triple, and so on. And in practice, what you do is that you start with a small basis set, you get your energy, and then you increase as much as you can. And you look how the energy converge with respect to the basis set. At some point, the energy won't change if you increase the basis set. Okay? And when you reach this, if you can reach it, because sometimes the Hamiltonian, there are so many Gaussians that you cannot even build the Hamiltonian. And then you cannot check convergence. But if it's converged, we call it the Hartree-Fock limit. Okay? So this is when the Hartree-Fock energy, the total energy, doesn't depend on the basis set that you choose. Okay? Okay, I answer your question. Yeah, good. So what's the issue with Hartree-Fock? Why do we need to go beyond Hartree-Fock? So the first one is that it's a ground state theory. So it gives us only the energy of the ground state, or an estimate of the ground state. And if we are interested in decay processes, we need to go to excited states. We need highly excited states. So that's one issue. The second issue is that there is no correlation. Okay. So a way to see the Hartree-Fock method is that each electrons move in the mean field of the other electrons. So sometimes Hartree-Fock are called actually mean field theory. Okay. So every electron moves in this mean field. Okay. And the correlation is that when electron moves, the others should react instantaneously, and this is not included in the Hartree-Fock. Okay. How we see that? So if you draw the electron energy as a function of the basis set size, so that means the number of Gaussian functions that you include in your calculation. So here you have small basis set, large basis set. So as I said, at the energy change until it doesn't depend on the size of the basis set. So this here, that's what we call the Hartree-Fock limit. Okay? And this Hartree-Fock limit is always above the exact energy. Oops, where is it? Ah, here you go. Okay? And this difference here, that's what we call the correlation energy. Yes, yeah, you always get lower energy if you include the correlation. That comes from the variational principle. Mm. Mm.
So, if I take helium,
Yes, yes.
if I did variational principle, applied the variational method sufficiently, it would lead us close to the exact energy.
If you do Hartree-Fock?
No, if I do variational, if I apply the variational principle.
Well, actually, Hartree-Fock is variational, but it's your ansatz that limits the energy. So the variational principle tells you that you can take any wave function, you're gonna always be above, right? But yeah, it gives just you are always above the exact. But now, how low you can go for a given wave function depends on your ansatz. Okay, your ansatz on the mathematical
Not the
form.
number of iterations, not the number
No,
of trials.
no, no.
On the basis set, it depends.
Yeah, it depends. Well, but even if you take an infinite basis set, okay, for Hartree-Fock, you'll never reach the exact energy because you don't, because it's this mean field, you are always above. So the Hartree-Fock, so the energy in the Hartree-Fock limit of helium, it's minus 2.86 atomic unit. All right, and the exact energy is minus 2.903, I think, something like that. So this difference here, that's the correlation energy. And this you can do whatever you want. If your wave function is described as a single determinant, you never go below minus 2.86. You never reach minus 2.9. Okay.
What is the difference between ground state theory and excited state theory? Is there any pattern that one can anticipate that this theory is going to apply only for ground state and other theory is going to apply for excited
Um, Well, actually, it goes the other way around. The methods are developed for. It's not like you have one method and you say, okay, can it work for that or that? It's the other way around. You say, okay, I want to describe excited states. I'm going to build my method to do that. So we know which method are meant for excited states and what are the limit. And we know which method are for. But if you just looking at the names of the method and so on, no, you cannot say okay, it's a ground state. But it's known. It's known because they were derived and developed for that purpose. Do I answer your question? Yeah. Okay. So Hartree-Fock is ground state, DFT is ground state. We're gonna look at CI. CI can describe ground state and excited states. Couple cluster is in this original version for ground state, but there are versions for excited state as well. So that's basically those kind of methods that are mostly used. Okay. In the realm of DFT, we have TD-DFT, time-dependent DFT, which are for excited states. So, but you cannot just anticipate this. You have to learn them, learn the limit of those methods. Why they are developed, what are they good for, and so on. This you have to learn. Okay. And actually, running the that's one thing that is a bit you have to be careful. Running a calculation with quantum chemistry package now are really easy. It's user friendly. You have interfaces and so on. So really, it's really easy. Now to understand the numbers that come out, this takes some expertise. Some expertise. It takes some time because you need to know if the method is good enough for that system, if the basis set that you use is large enough, and so on. And for that, you need some years of practice. So that's really now what quantum chemist has to learn is, when to use this method, when not to use this method, and so on. Not really how to do it. How to do it is really simple. Yeah, it's like ChatGPT. It's really as simple as that. Yeah. All right. Other questions? No. All right. So how do we go beyond this ground state description, and how do we include correlation? As I started to answer, there are plenty method for that, and every day people develop new method for that. Okay. Lenz has spent a lot of time developing this kind of or one kind of method relying on Green's function and so on, and it's still under development and so on. I'm not going to talk about those methods. I'm going to talk about, let's say, the most standard, probably it's the first one that was developed and the most standard one, which is configuration interaction. So this we call post-Hartree-Fock method. So all the method that goes beyond Hartree-Fock. And one of them is configuration interaction. We call them CI. Because as I said, we like acronyms, so I'm going to call them CI. And now what you do is that you write your electronic wave function as your Hartree-Fock determinant, okay? But you're going to add a bunch of other determinants to include for correlation. And how you include them, you'll go by class. So you're going to include single excitation. So it means that you're going to take one electron from your occupied orbital and put it in the virtual, okay? But you can also do double excitation. You take two electrons from the occupied and you put them in the virtual, 3, 4, and so on. So you have all this class of CI methods, CIS, where you include only single, CISD, when you include single and double, and so on and so on. Okay? So you write it like this. Oops, sorry. Um, yeah. Okay, so what I wrote I wrote here is this ansatz. So that's the Hartree-Fock here in the beginning, determinant. Then you have the single excitation. So I take the electron from the J occupied electron and I put it in the A unoccupied orbital or virtual orbital. Then you have all the determinants where you take one electron from J, one electron from K, and then you put it in the virtual orbital A and B, and so on and so forth. You can do it for triple and so on. Okay. If you include all possible excitations, so for example, let's say you have 10 electrons, and then you take all these 10 electrons and you put them in the virtual, this is what we call full CI. And if your basis set is large enough, you basically get the exact energy. Okay? But full CI is far too expensive. Okay? Because the number of determinants, it grows exponentially and then your matrix gets too large. Okay? So usually we have to truncate this expansion. Okay? And most of the time we truncate it at the double excitation. Okay? So what we do is that we take only this part here, and this we call it CISD. So it's configuration interaction with single and double. So you always very often find this kind of method. Okay? And if you do that, then you start to include some correlation. So for example, if you take the example of helium, now if you have a large basis set, with TISD you get minus 2.89, I think, something like that. So you're still not in the exact, but you're getting really close. Okay, so the energy for CISD for helium is minus 89 atomic units. Cool. So you're getting really close to the energy. Okay. So what you do is that you do your hard set CCPV DZ. Okay. You get your occupied orbitals and your virtual orbitals. Okay. And then you build all those determinants where you excite 1 or 2, and you build your Hamiltonian, your CI Hamiltonian, which starts to be quite big, and you diagonalize it. Okay? So you have your HCI, and when you diagonalize it, because now your Hamiltonian matrix is in the size of the number of determinants that you have included, you're going to get more than one energy, right? And you get excited state energy, basically. Okay? So the size here equal the number of determinants that you have included. So let's say, yeah, I don't know. It depends of your basis set, but what you get then is the energy. So you get a better description of the ground state energy plus excited state. Exactly. Yes. So if you include all possible determinants, you get the total correlation energy. When you truncate it, you take you have an approximation, an estimate of your correlation energy.
Now is how this correlation energy is connected to the excitations here.
Uh,
Is it accounting for the exchange integral and Coulomb integral?
no, because in Hartree-Fock you have all the Coulomb and the yes. So if you again to answer your question, if it's in terms of physics, this determinants what all allow is that each electrons now they move when the other one move. Okay, but that includes in the correlation you have the Coulomb and the exchange can do that. But in the Hartree-Fock you also have the Coulomb term but it's the mean Coulomb term that you have. Okay. Now you get you get that if you take two electrons and when this one moves, then this one reacts also. Okay. It doesn't wait that the whole thing has moved, take the mean, and then start moving. They really are correlated. They move with respect to each other. Okay. And they can exchange and so on. Okay. Yeah. So this is what adding these determinants allows you to do.
Sir, does this ionization part of this configuration interaction consider what sort of ionization mechanisms is involved to ionize the molecule?
There's no ionization here. Well, so what you get here is the energy of the system. So, for example, let's take helium. You're going to get the energy of 1s2, 1s2s, 1s2p, and so on. And depending of your basis set, at some point you cannot describe all possible excited states, but you get some. Okay. So in principle, you get only states of helium. Okay. But when you diagonalize your Hamiltonian, in this energy here, you're going to get some states that are above the ionization potential of helium. Okay? So that's a good question. So if I draw this energy here, as I said, for helium, well, you get the ground state, which is minus 2.99. Okay? Then you get some excited state, for example, 1s2s, and so on. And here you have this ionization potential. So you have helium plus, which is minus 2 atomic units. This helium plus, you don't get it in the calculation. It's something that I draw here to illustrate what I'm going to talk about now. Okay? And you get also states that are here, right? And those, for us, that's our pseudo-continuum. So it's like helium plus one electron in the continuum. But we describe those two together, the helium in the continuum and the helium plus. Okay, they are described in the same way. It's not like you get the state of helium plus. You still get the state of helium. Okay, and it's pseudo-continuum because for several reasons. The first one is that it's not the right boundary condition. I'll talk about it a bit later. Because now we use Gaussian functions, so those are L-square functions. So it means that they die and they are normalized to 1. But the continuum, the electrons should have a different boundary condition, different normalization. Okay, so we cannot describe them completely. And they are discrete level. Okay, because you have a finite number of determinants. So you don't get really a continuum. You have discrete energies. Okay. So are there other questions about quantum chemistry? Because now I'm going to talk about resonances or final theory. So if there are questions about quantum chemistry, it doesn't have to be on what I said. If you have other questions on quantum chemistry, I can try to answer, or Lens and we can try to answer.
You
Yeah.
could just illustrate how it is done in the quantum chemistry package, maybe step, just the algorithm.
Uh,
In the quantum chemistry package, how let's say post-Hartree-Fock calibrations are performed, for instance.
so what every step that you have.
Just one illustrative calibration of
I prepare some illustration, but more for the final theory part. But I'll show some part of the quantum chemistry, so maybe that will help later. Well, maybe I can show you now at least the quantum chemistry part. Yes.
just to see visually how this works.
Um, wait. I'm disconnected. I have to reconnect.
Anybody probably wants to use have a glass of water, maybe for a 5 minute.
Yeah, we can have a break now. Yeah. Okay, good. Sounds good.